Okay, so in the last lecture, we were discussing about some integration examples for calculation of center of mass of continuous mass distribution. Okay, so we saw some examples of application of those formulae that we got from integration, and then we had moved on to collisions. So we discussed about the different types of collisions, as in head-on collisions and oblique collisions. Then we went on to define what is a perfectly elastic collision, right? One where there's zero loss of kinetic energy. Okay. And that was about it. Okay. We saw the definition of perfectly elastic, perfectly inelastic, and partially inelastic, or what we generally just call inelastic collision. So let's take it from that point onwards today. Okay, so let's discuss some general properties of the head-on collisions. So what we see in the case of head-on collisions is that whatever be the situation with energy, whether kinetic energy is conserved or it is lost, momentum is always conserved. So if a particle of mass m1 collides with another particle of mass m2, both moving along the same line with velocities u1 and u2, this is before impact, such that after impact, this one's velocity becomes v2 and the particle m1's velocity becomes v1. Okay, then what we saw is that m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is the momentum conservation equation, which is universal for all head-on collisions. But now, in case kinetic energy is conserved for a perfectly elastic collision, kinetic energy is also conserved. So we have initial kinetic energy is equal to final kinetic energy. Okay. So now solving equations 1 and 2, we also get the general equation that v2 minus v1 is equal to u1 minus u2, or the separation velocity is equal to the approach velocity. We get this important result for the case of perfectly elastic collision. Okay, so we have discussed how this solving happens. Okay, now we will see that in the case of inelastic collision, in the case of inelastic collisions, there will be some loss of kinetic energy. So the final kinetic energy will be less than the initial kinetic energy. So when we solve for that condition, the result that we'll get is that the separation velocity after impact will become less than the approach velocity instead of equal to. So kinetic energy is dissipated. Some of the kinetic energy is lost. So that basically means that the final kinetic energy of the system is less than the initial kinetic energy. So half m1 v1 square plus half m2 v2 square is less than this. So when we solve for this condition now, along with the momentum conservation equation, what we'll realize is that now the separation velocity becomes less than the approach velocity. So anytime there is loss of kinetic energy, the particles don't separate as rapidly as they are approaching each other in the case of so this will finally give us the result that v2 minus v1, instead of being equal to, it becomes less than u1 minus u2, or the separation velocity becomes less than the approach velocity in the case of the inelastic collision. People who are joining the meeting right now, please be on time from next time. I will not admit people after 7:40. Okay.
Sir.
Yes.
Sir, it was not accepting the password. I wrote it in the chat.
Well, I don't know, because more than 35 people have been in the session since the beginning. So probably
so
you can
password
reinstall.
basically it is actually wrong. It's supposed to be 0901. It's just showing 090. So that's why people aren't able to join, I guess.
Password is correct. People
No,
have
sir, even
entered
I
through
tried
that.
to join with password 090. The password that's showing on chat is 090, and it's
Yes,
not
sir.
the correct one.
Actually, everyone
0901
has
is the correct one.
entered with the link.
Anyway, please be on time from next time.
Done, sir. Written this.
Okay, so now we will define another parameter for collisions, for head-on collisions, which is called the coefficient of restitution. So the coefficient of restitution is denoted by the symbol E, and it is simply defined as the ratio of the separation velocity after impact with respect to the approach velocity before impact. Okay, and that becomes, in terms of the original sign convention and diagram that we have drawn, it becomes this quantity. This is in relation to the diagram and the parameters that we've seen before. So E is equal to 1 for a perfectly elastic collision. And E is greater than 0 but less than 1 for what we call an inelastic collision. And E is exactly equal to 0 for what we call a perfectly inelastic collision. Because what happens in this case is that the colliding particles stick together. So that means their final velocities are common, which means that the separation velocity is 0, which means that the coefficient of restitution is 0. So these are the three cases of the value of coefficient of restitution which becomes significant. Okay, so let's see how we can utilize this in a numerical situation.
Sir, 1 more minute, please.
Okay. Okay, done.
Yes, sir. Yes.
Okay. Okay, so let's look at a numerical example. So we have a particle of mass 2 kilograms, which is moving at a speed of u1 like this, of 5 meters per second, approaching another particle which is lighter and of mass 1 kilogram, which is moving away in this direction at u2 equal to 2 meters per second. So we have to find, so they make a head-on impact, m1 and m2. Find their final velocities if E is equal to 1, that is, it's a perfectly elastic collision. Okay. Or if E is equal to 0.5, it is an inelastic collision. Okay. And also find the percentage loss in kinetic energy. Okay. Third case, if the percentage loss in kinetic energy is 20%, find V1 and V2 their final velocities, and also find the value of E. And fourth and final case, if E is equal to 0, that is, it is a perfectly inelastic collision. Anybody got the answer for the first part?
V1 3 and V2 0.
Let me just check.
सर V1 3 and V2 6 आया.
Yes, that one is
Okay,
correct.
sorry. I made a sign.
V2 has to be greater than V1, no? But yes, that's correct. Plus 3 and plus 6.
I made a sign mistake.
Yeah.
Again.
So the first particle slows down from 5 meters per second to 3 meters per second, and the second one speeds up from 2 to 6. And you can see that if you look at the kinetic energy, it will be a conserved quantity. And if you look at the separation velocity for those values, you will get it equal to the approach velocity. Okay, very good. Work out the second part now. So I'm just showing you the solution of the first part for the rest of us. This is before impact. And suppose this is after impact. So perfectly elastic means E is equal to 1. So separation velocity is equal to approach velocity, which means that V2 minus V1 is equal to U1 minus U2. Okay. So here V2 minus V1 will become 3. That's our first equation. Okay. And momentum conservation, that's our other equation. So M1 V1 plus M2 V2 is equal to M1 U1 plus M2 U2. So that here will become 2V1 plus V2, okay, is equal to initial momentum, which you can see is 10 plus 2, right, 12. So now if you solve these two equations, you will get the value of V1 and V2. Okay, so let's look at the second part now. The second part, we have taken the coefficient of restitution as 0.5. So the difference here will be that the separation velocity will be 0.5 times the approach velocity. So V2 minus V1 will be 0.5 times U1 minus U2. So this equation changes to V2 minus V1 is equal to 1.5. Okay, whereas momentum conservation still gives us the same equation. There's no difference in that equation. So 2V1 plus V2 is still 12. So now solving these, you get V1 and V2 as something different now. Yes, that's your answer is correct. Yes, very good, Akshat and Soham. Your answers are correct. So once again, you can see that if you just subtract these two equations, this time you get 3v1 is equal to 10.5. So v1 comes out to be 10.5 by 3, which is 3.5 meters per second. And correspondingly, v2, when you substitute, will come out to be 5 meters per second, because the separation velocity is 1.5. So now from this, you can see the percentage loss in kinetic energy by calculating the final and initial kinetic energy. So from this, you can see that the final kinetic energy of the system will come out to be 3.5 square plus 5 square by 2. So that is 49 by 4 plus 25 by 2. So that we can write as 50 plus 49. So that is 99 by 4 joules. Okay, so that is this is the final kinetic energy. Whereas the initial kinetic energy, that is equal to okay. So the loss in kinetic energy. So since we are writing it as a loss, we will write it as initial minus final. So you can see that there is a loss of 29.5 minus 4.75. So that is how much now? Sorry, 4.75, right?
4.7. Yes.
So this is the loss itself. So when we convert this into a percentage loss, we have to express it as a percentage with respect to the initial kinetic energy. So the percentage loss is equal to the loss divided by the initial value into 100. Okay, so that is in this case the loss in kinetic energy divided by the initial kinetic energy expressed as a percentage. So that is nothing but 4.75 expressed as a percentage of 29.5. Okay. So this is the percentage loss in kinetic energy. Okay, so move on to the next part.
KE initial will be 27. Now, matlab half M2 is 1 and U2 is 2 square.
M1 is wait, just let's see the values once more better. Okay, yeah, what is the initial kinetic energy? Let's understand here. It is half into 2 into 5 square, that's 25. Okay, plus half into 1 into, oh sorry, 2 square, my mistake. Yes, so it is 25 plus 4, sorry, plus 2. Yes, I've taken it 3 by mistake. So 27 joules. Yes, we'll make that correction. Okay, so this should be 27 joules. Is the final value of kinetic energy all right? It's correct.
Yes, sir.
Okay. So this is coming out to be how much now? The loss 27 minus 24.5. Sorry, 24.75. So 2.25 joules of kinetic energy loss. Okay. So a percentage loss will become something different now.
Sir, in KE final, 3.5 square will be 12.25, right?
Hmm? Yes. 12.25, that's correct. 12.25 plus 25. Okay. Sorry, 12.25 plus 12.5. So that's how we are getting 24.75. Okay, so anyway, let's convert this into a percentage. So I'm getting a 8.3% loss. Okay, so complete this part and let's come to the third part. Now in the third part, coefficient of restitution is unknown, but the percentage loss of kinetic energy, that is given to us, and that is how much? 20%. Okay, so again, so this time one equation will be the momentum conservation equation, but the other one will not be the coefficient of restitution equation, rather it will be the kinetic energy equation. If there's 20% loss, that means the final kinetic energy is 80% of the initial kinetic energy. 80% means 4/5. So that's how we'll interpret this statement now. So this statement now, this implies that the final kinetic energy is 80% of the initial kinetic energy. That means half m1 v1 square plus half m2 v2 square is 0.8 times half m1 u1 square plus half m2 u2 square. Okay. So v1 square plus v2 square by 2 is 0.8 times the initial kinetic energy, which we already seen. It's 27 joules. Okay. So this is one equation, and momentum conservation. Giving us our second equation, that okay, so this system of equations has to be solved now. Okay, so solving this is a bit lengthy, but anyhow, let's see how it is done. So basically, you'll get a quadratic equation when you substitute this here. Okay. So you can see that V1 square plus V2, which we can substitute as 12 minus 2V1. So this is equal to, now if we just multiply 27 with 0.8 gives us 21.6. So we get V1 square plus 4V1 square plus 144 minus 48 V1. So finally we'll get an equation like this. 6 is the coefficient of V1 square, okay, minus 48 is the coefficient of V1, plus we will get here 144 minus 20, double of 21.6. Okay, so we get, so this is our quadratic equation for V1. So minus B plus minus root of B square minus 4AC divided by 2A. So if you open up this term, so we can probably take a few things common also, but anyway. Okay, so this is giving us
An imaginary value.
an imaginary value. Okay, so what that means? Okay, so this is not possible. Okay, so what that means is that 20% kinetic energy loss is not possible. Okay. But I'll explain to you why that's not possible, because when we look at the case of the inelastic collision, we'll see perfectly inelastic collision. Okay. Okay. Basically, that means that the maximum loss in kinetic energy will be something greater than, sorry, will be less than the 20% loss. Okay. But for example, instead, if we were to take, if loss was, let's say, what is the percentage loss we got here? 8.33. So let's say it is something like 5% loss. Okay. Then we would have got a different equation numerically. We would have got final kinetic energy is 0.95 times the initial kinetic energy. So this quadratic equation would have changed, and accordingly, what would have changed is this term, this discriminant term would have changed. So we'll get some value. Okay. Now to save time, I will not get into this. We'll look at another question where the values are simpler. But the answer to this will simply be this, that this is not possible. Okay. What this equation is showing us, that 20% loss is not possible. Okay. And the reason for that is this only, that maximum loss in kinetic energy, and that we will see through the next part. Okay. So next part, let us solve the situation where we have the perfectly inelastic collision, E is equal to 0. So this is a very easy part to solve because final velocities are equal. V1 is equal to V2. It becomes one single combined object. The two particles stick. So we just have to write a momentum conservation equation to find the final V. But when you find that final V, you can also show that how much is the loss in kinetic energy, and you will see that that is less than 20%. So that will again verify what result we are getting here. The 20% loss in kinetic energy is not possible. Yes, that is correct, Akshat. So solving the E equal to 0 case, we'll see that V1 is equal to V2, equal to V, because they stick together. So after impact, they become like one combined object. Is moving at a velocity V. Whereas before impact, like this. So M1 U1 plus M2 U2 is equal to M1 plus M2 into V. So this momentum we had seen was 2 into 5 plus 1 into 2. So this becomes a combined mass of 3 kg into V. Okay, so that you can see comes 4 meters per second. So now you can also see that the final kinetic energy becomes this. (24 joules, right? Okay, so the percentage loss now you can see is initial kinetic energy we had already seen was 27 joules now. Okay, so this much loss is there. So this also shows us the maximum possible percentage loss for this collision is 11.11%. That again reinforces this, that 20% loss is not possible. Yes, very good, Som. Okay, people, so hope this is fully clear. Now we'll look at another thing that we can do with this concept of coefficient of restitution and all. We can develop some general formulae for head-on collisions. Given the value of the coefficient of restitution. This is very simple. It's just, instead of numerically solving for a particular case, we solve parametrically the two equations. So the initial situation is like this. And the final situation after impact is like this, let's say. So we have M1 U1 plus M2 U2 is equal to M1 V1 minus M2 V2. Okay, which we can also write like this, that M1 into U1 minus V1 is equal to M2 into V2 minus U2. Okay, and we have separation velocity upon approach velocity is equal to E. So this equation can be written as V2 minus V1 is equal to E times U1 minus U2. Okay. So for example, here this can be written like this, and we can substitute this here and then solve. So on solving, we get a general formula like this, and it's worthwhile to actually memorize these formulas so that you can use them directly in questions. So the way to remember the formula is that there are 4 coefficients involved. Okay. Because each of the terms is a coefficient into U1 plus a coefficient into U2. So write this symmetrically. Okay. Now all the coefficients are expressed in a fractional form, and they have common denominator of M1 plus M2. It's very easy to remember these coefficients. Okay. And the cross diagonal terms, that is these two terms, are M1 minus E times M2, and this one is M2 minus E times M1. Okay. And these two diagonal terms are also symmetric, but they are M2 into 1 plus E, and this one is M1 into 1 plus E. So this is like a set of general formulae. Yeah, this is supposed to be plus. Okay, so this is like a set of general formulae. And it's not just that, we can apply the formula directly in questions and save some time, but also it helps us in the analysis of collisions, which we'll see next. The analysis of various different cases of collisions, we'll see. So first make a note of this. Okay, so let us look at, yes, the formula is for the final velocities v1 and v2 in terms of the initial velocities u1 and u2, and of course the coefficient of restitution also. So let's understand some of the special cases that we can analyze using these formulae. So first of all, you can see that if we have the case of a perfectly elastic collision of identical masses m1 equal to m2, if we have this situation, then what happens from the above formula, you can see is that v1 becomes u2 and v2 becomes u1. That means they exchange their velocities. Okay, so as a simple example, suppose we have two blocks of same mass and they are moving, let's say like this. Okay, so we will substitute m1 equal to m2 equal to m and u1 as +3 and u2 as -1 meter per second. Now if m1 and m2, or if a and b make a head-on perfectly elastic collision here, then what will happen is that after impact, their velocities will become like this. Okay, so they exchange their velocities. So you can verify this by substituting in the formula, or you can verify by using the fundamental equations that momentum is conserved and separation velocity is equal to approach velocity. So here you can see that what is the momentum of the system initially. It is plus 2m, whatever the value of m is. Okay, and what is the approach velocity? You can see it is 4 meters per second. Okay. But similarly, you can also see that what is the final momentum and what is the, from this you can understand the final momentum is again plus 2m. That's correct. Okay, and the separation velocity is again 4 meters per second. That's also correct. And similarly, if you work out the kinetic energy also, you'll see it is conserved. So this is the first special case that we should remember, that if perfectly elastic collision of identical masses happens, then they exchange their velocities after impact. Okay, now the second important case to remember here or to analyze through these formulae is a situation like this. Just a moment. Yeah, so the second special case to remember here is that if we have a situation like this, where M1 is coming in with some velocity and colliding with a second body which is at rest, and the collision is perfectly elastic. Okay, so then what happens here is that V1 becomes M1 minus M2 upon M1 plus M2 into U. That is U1 is equal to plus U and U2 is 0. Okay, and E is equal to 1, this special case. Okay, so this gives us this, and V2 becomes 2M1 upon M1 plus M2 into U. So from this formula for U1, now we can see that there are two cases. If the colliding body is heavier than the body at rest, then V1 is positive. Okay, but if M1 is lighter than M2, then what happens is that V1 becomes negative. That means M1 recoils back after impact. Okay, so after impact, M1 will have a V1 which is negative. Whereas in this case, M1 continues in same direction, but with reduced speed. Okay, so note down this special case and let's look at an example of this. So M1 makes a perfectly elastic head-on collision with a stationary mass M2. Okay, after impact, M1's speed is 6 centimeters per second. So find the value of M2 and its final velocity. Okay, so note down this special case and then try out this question. We'll discuss.
So 6 centimeter per second in the same direction.
That is not given. So basically you have to consider both the cases. You understood now?
Yes, sir.
Okay. So that is where this analysis becomes important from above. Okay, there are two possible cases. And accordingly, you will get two different sets of answers for mass and all that, right?
Yes, sir.
Yes, very good. Soham, your answers are correct. Okay, so we can understand that if it's given to us that speed is 6 centimeters per second for m1, so we can take two cases. V1 can be plus 6 and V1 can also be -6. Okay, so in this case it recoils. Okay, so that basically means that M1 is lighter than M2, and in this case it does not recoil. This is the case where M1 would be heavier than M2. So let's look at each of these cases. So if our V1 is +6 centimeters per second, so you can see that before impact, this was coming at 12 centimeters per second. Okay, so the approach velocity was 12 centimeters per second. Now after impact, after having collided here, if M1 continues but with a reduced speed of 6 centimeters per second, M2 will have to go off with some velocity. So separation velocity here will become V2 -6. Okay. Now because E is equal to 1, so separation velocity is equal to approach velocity. That means, okay, so this separation velocity has to be 12. So that means in this case, V2 has to be how much? 18 centimeters per second. That's one thing. Okay. And also V1 is M1 minus M2 upon M1 plus M2 times U in this case. Okay. So +6 is equal to, now how much was our M1? Two kgs. Okay. So 2 minus M2 upon 2 plus M2 is 1/2. So this is the first case. Okay. Now similarly in the second case, you assume that V1 is -6 centimeters per second. So before impact, this is the case, but after impact, okay, and solve accordingly and you'll get. Yes, Akshat, your answers are correct. Okay, so in this case, again, you can see that the approach velocity is 12. The separation velocity is now v2 plus 6 because they're in opposite directions. So E is equal to 1 means that v2 plus 6 is equal to 12. So in this case, v2 is 6 centimeters per second, because v1 with sign convention is minus 6 centimeters per second. And now we can use either of the two formulae. So minus 6 is equal to m1 minus m2 upon m1 plus m2 into u1. So minus 6 is equal to this factor now. So 2 minus m2 upon 2 plus m2 is minus half. Or we can say that 4 minus 2m2 is equal to minus of 2 plus m2. So we have m2 is equal to 6 kgs now. So that is the second case. Okay, so just make sure you note down both these properly. So there are two possible solution sets for this. Okay, if the final speed of the first body after colliding reduces to 6 centimeters per second, there are two cases possible. If it's recoiling, then it's doing what is happening in case 2 that we have taken. If it's continuing in the same direction, then it's case 1.
So can you scroll upwards for a minute? Sir, done.
Yes. So you can also calculate V2 using that. Okay. So here I have calculated V2 using, separation velocity is equal to approach velocity, but you can also go with the formula based method. So once you're seeing that M2 is this much, you can see that from this we can see V2 is 2m1 upon m1 plus m2 into u1 in this case, because u2 was 0. Okay. So it will become 2 into what was m1 now, 2 kgs, right? So 2 into 2 divided by 2 plus 2 by 3 times u1, which was 12. So you can see this is 4, okay, to 12. So 2 upon 4 by 3 to 12. It's 18 centimeters per second. That's another way. Okay. Or from this V2 also we could have seen that V2 is 2m1 upon m1 plus m2 u1. So from this we could have calculated m2 also. So we could have done this also. So from this we would have got m2, and that m2 would have been 2 by 3. So we have all these options. Okay, can use a combination of all these concepts. Okay, so before we conclude today's session, people, one additional thing we'll look at, and that is when there is a collision of a particle with a rigid surface, instead of colliding with another body or another particle, if we have this situation, collision of a body or a particle with a fixed rigid surface, like a ball bouncing on the floor. And the surface is not elastic, okay, like a rubber sheet or something. It is a rigid surface, like a wall or a rigid floor, that kind of situation. So in this we'll take the first case only today, which is the what we call the normal impact. So normal impact means the object that is colliding in the normal or perpendicular direction. So imagine a ball bouncing, something like this. So if comes and collides with a velocity v0, where v0 is the impact velocity, and that should be normal, or that means perpendicular to the surface. So this is our fixed rigid surface. So what happens on impact is that the surface ends up applying an impulse on the object in this sort of direction. Okay. So this is an equal and opposite impulse acts on the surface, but this impulse is absorbed by the ground, by earth, because the surface is fixed to the earth. Okay, so that doesn't cause the surface to start moving because it's a fixed surface, but instead now, as a result of the impulse on the body or on the particle which came and collided, the particle's momentum will tend to reverse in direction, and after impact it will have a velocity. So this velocity will become E times the approach velocity, where E is equal to 1 for perfectly elastic, 0 loss in kinetic energy. E is between 0 and 1 for inelastic collision. And E is equal to 0. So the object sticks. Okay. So in this case, there's 100% loss in kinetic energy. So these are the three cases. So as you can see, it's a very simple derivation. I mean, it's a very simple set of concepts and derivation. So this velocity v is after impact, and this is also normal to the surface. So J here is the collision impulse. Okay, so with that we conclude today's session. Next time we'll look at applications of this, and also we will look at the second case, which is an oblique collision, where the particle can come and hit the surface in a diagonal sort of manner, where it has both tangential and normal component instead of just the normal velocity. Okay. So that and more coming up next time. That's it for today's session, people. Wish you all the best and have a nice day.
Sir.